I'd like to add to Suzanne's acknowledgement, my acknowledgement of the Gadigal people of the Eora Nation, and my respects for the tens of thousands of years of cultural transmission, teaching and learning that's happened on their sites and the sites of Aboriginal people throughout Australia. It is an amazing pleasure to be here with you all, and thank you all. I realised that there was some ticketing and other kinds of sort of wait list issues for some of you. Thank you for bearing with us and all of that. It's particularly important for me because this is a first manifestation of our visual research partnership, indeed, as Suzanne said, and I won't repeat too many of that, but it is also important because, as some of you will have noticed from the plaque on the wall as you came in, if you came in up from the rocks, from the harbour, that the Power Gallery of Contemporary Art was the first name for this institution. And as Suzanne was saying, it's a complex tale, as we all know, but I think it is very important that the presiding visions of what the MCA might be began to be articulated amongst other places, at the University of Sydney and more specifically at the Power Institute. And I want to acknowledge Terry here, who is here and he will speak later, but also the late and much missed Virginia Speight, who really was one of the, not only a magnificent art historian, but one of the motors behind the idea and the persuasion and all of the things that it took to think through what it might be to exhibit modern contemporary art here in Sydney. I'm very excited, though, for the future. The past might be complicated. I think the future will be more exciting than complicated. Of course, the MCA is about artists and art practice, as Suzanne was saying, and the MCA is never shy of a challenge to bring complex acts of seeing into the galleries. I want to congratulate Suzanne on all the wonderful shows that are going on right now. I mean, you can just take a slice through what's going on right now and you will see how ambitious and exciting the programme is. One of the prime impulses behind the project that this symposium forms a part of, the Visual Understanding Initiative, is something I perhaps will just spend a couple of minutes explaining before we run into what I want to say at the beginning of our first panel. This initiative, which was seeded in large part by a very generous grant from Penelope Seidler, who I'm delighted is able to join us, and has been continued by other very generous funders, is designed to help us broaden our scope. And when I say us, I mean maybe us at the Power Institute / Department of History of Art, beyond our usual ways of research, teaching and dissemination, to explore how we see in social, cultural, even in species terms, in new initiatives in teaching, new collaborations in research, and new forms of digital publication, diffusion, and communication. Broadly, in this initiative, we're thinking through large guiding pillars, if you want. I mean, there's sort of, that sounds all a bit sort of ancient Greek, I know, but one of those is how we see now, which is exploring, excuse me, new questions of and problems of what, how, and where we see, and we're going to explore many of those issues in a moment, from the nano to the galactic scale, involving us in research with scientific and social science colleagues, combining bedrock visual analysis skills with insights from colleagues across disciplines. And some of the panels you're going to be hearing right now, you're going to hear a panel which attempts to think that through. Our second pillar is actually called First Nations Ways of Seeing and Knowing. And that pillar, which was very much the brainchild of Stephen Gilchrist, who's right here with us. How fantastic to see you, Stephen. I'm sorry, I couldn't pick you out through the camera there. And is very much reflected in the exciting panel we're going to have on Torres Strait Islander ways of being, seeing and knowing tomorrow. And that will continue to be a guiding force for everything we do. And we obviously need help and community and thoughtful interactions to make that happen. And we're delighted that it's a pillar. And the third of those pillars is visualizing ideas, something you'll hear about later this afternoon, very much driven by my colleague and co-lead on the Visual Understanding Initiative, Marnie Williams, who this takes seriously the need for us to think about how we communicate visually. Specifically, how do we make new thoughts visible? How do we enable communication, interactive, community-driven or research-driven frames of visual communication? And I think you'll hear a lot more about some of the ways this might be happening. So these are very big questions, and of course, this is not the answer to everything research grant. This is the beginning of a large enterprise, and one which we might, and I'm going to say a little about that in a few seconds, might find a little daunting, some might even say hubristic, but we're going to give it a try because as we've heard, it is really important that we connect ourselves to the living, breathing heartbeats of research across many disciplines, because we have fights to fight and struggles to struggle with, and we're going to need all the resources at our intellectual disposal. So I would just like to finish this thanks and explanation bit by adding my special thanks to everyone here at the MCA who has made such an amazing effort to sort of get us all in, make us all comfortable, make us all welcome, from the top, from Suzanne and Lara, down through to all the staff who have helped put this all together, including all the technical and welcome staff here, many of whom have been mentioned already, but I want to thank them again. And I do want to add my special thanks to my wonderful power team, which includes Katrina Grant, Lucky Thompson, but especially on this occasion and for these few days, Marnie Williams and Nicholas Croggan, both of whom are chairing panels over the coming days, and both of whom, in one stage or other, and as we brought it together, have really made these 3 days possible. So Marnie is the co-leader of the project as a whole, and especially thought through how we might integrate some ideas of visualization into this event. And of course, I would say that Nick Croggan is the presiding genius of this event. So I want to thank him particularly. Right, okay, thank you all. And I'm going to, I don't know if you noticed, yes, please come in. I can rabbit away while you come in, and you won't miss much, I promise. Whoops. So in the program it said, welcome, and what is vision? Now, I can't promise, for my section, I can't promise to entirely answer that question, but before we're going to transition to our first panel with our wonderful speakers, I'm just going to say a few, framing words about sort of how we all ended up here, if you like, and there will be lots of different views on these, but I want to start with an image with which some of you may be familiar. About almost exactly 25 years ago today, thanks in great measure to the good offices and frantic negotiations of power, and Terry knows more of this than I, on a packed stage at Sydney Town Hall and in other venues across Australia, the late French philosopher Jacques Derrida mused on, among other topics, it wasn't the only thing he talked about, what he called the need for the deconstruction of the widely held premise that vision, seeing and knowing, seeing as knowing, is at the heart of Western thought. And that's just to cite the transcript that Power made. It might seem then, perhaps, that in 25 years we've totally failed to listen to him. Here I am giving the title Visions to an event and promising to probe vision. And you might be asking, well, how aren't we just re-privileging and hierarchizing what he strove to contest or to pull apart? And I suppose my answer would have to be a little bit yes and no, but unashamedly, I'm hoping this panel and the whole conference will ask again questions of how we see. But we'll always bear in mind that as we do so, as we explore vision, we're also exploring what limits our vision, what motivates it, what diverts it, what deceives it. And we're going to start this whole occasion with a panel which pairs artistic practice and scientific research, demonstrating that one way we're contemplating the question of vision in the 21st century is through engagement with scientific inquiry, much of which was only in its infancy when Derrida stood up and pronounced about the primacy of vision. Inquiry which is peering into the nature and limit of seeing, of the visual apparatus and the brain to which it's connected in many exciting ways, and is spurring a range of artistic and philosophical inquiry, as well as obviously a plethora of scientific response. So, we have, the giants of the neurobiology of vision who are writing about what connects seeing and knowing, if you like, sort of taking up Derrida's challenge. But we also have philosophers in traditions that more we would recognize as humanities traditions, and Benchen Ané is one of those who are trying to think through what perception might be if in ways which we would recognize through the history of philosophy. So I hope this panel that you're going to hear will demonstrate
that both the science of seeing and seeing science has the power to confront us, that the deconstruction task may be even larger than Derrida imagined. We're not merely deconstructing a primacy of vision in Western knowing, or even that Western knowing itself, but we're also asking the question of what seeing actually is, whether anything about the act of seeing can be taken for granted. And as we'll hear, fundamentals of vision and art making, from movement to colour to depth to the order of the senses, have all come under some new scrutiny from new methods of exploring our perceptual apparatus. And I'm going to leave Anina to talk much more about this. But there are lots of ways that you could say, well, what does that mean? But, while Derrida was over here expounding on the dangers of an intuitive understanding of vision, or indeed of any of the senses, and that was one of his main points, that we should always doubt our intuitions. And the trouble with seeing is that, it seems like the most intuitive or naturalizing thing. But the experimental psychologists, and this is familiar to the scientists among you, Simons and Chabris, were publishing a landmark paper in Perception, and it's famously and slightly entertainingly called Gorillas in Our Midst, and sustained inattentional blindness for dynamic events. And this really more for fun than to prove a point here is, it was built on a famous experiment by previous experimental psychologists, Neisler and Becklin, about selective attention. And they wanted to work out what was inattentional blindness. And you may have all seen this before. I wonder if you have. If you haven't, and are horrible. Just take a minute or so to have a look at this and follow the instructions. Okay, so obviously now it's almost impossible, because there's an article called Gorillas in Our Midst, to not know that. But when they first ran the experiment, more or less 40-something% didn't say they didn't notice. But you may not have noticed that somebody left the stage during that, and that there was a complete change of colour in the background. And let's not rewind and watch it again. So I only mention this because attention and those related questions have become some of the most important zones of our inquiry. We may not think about it in the same terms, but there is a social concern of attention span. We're concerned about how our attention is directed and misdirected politically. We're concerned about the mining of our attention, and the question of visual attention, among with other related issues, such as motivated seeing, which Emily Balcetis and colleagues have talked about. We see different things if we are provoked, nudged, or even if we are strongly effectively minded to see it. The famous sports games, did you see the referee make the wrong decision, sort of paradox. Cognitive dissonance leads us to really see differently. This is at least one of the things that were discussed. So I'm mentioning this because experiments and new equipment and techniques that probe human seeing are not just there to produce scientific papers and pretty patterns in, what lights up here and what lights up there. They have direct social, medical, of course, but also cultural consequences. And in a way, socially aware and scientifically equipped researchers are helping to nuance or qualify what we have seen, or what has been seen as kind of slightly tediously seen as a fundamental of recent debates about what seeing is, which is sometimes known as the vision debate. I know whether perception is a hardwired biological constant, or whether it's always constructed and historically configured as a kind of set of behaviors, right? That's a debate that's been joined from various angles by such luminaries as Régis Debray and Jonathan Crary and Arthur Danto. This is just from the, if you like, from the aesthetics point of view. Art history, it has to be said, has traditionally entered this debate from the side of the social construction thesis, as many of you will know. Perhaps one of the more famous early pronouncements even founding statements of academic art history came in Heinrich Wölflin's Principles of Art History, well, as the translated title has it, in which he says, vision itself has its history, and the revelation of these visual strata must be regarded as the primary task of art history. Now, Wölflin's slightly now distrusted Hegelianism, his tendency to talk in terms of folk and nation, make his work perhaps hard to read or get excited about. But Wölflin's influence on a generation of more materialist-oriented thinkers, as we know, Alois Riegel and then Walter Benjamin, is pretty clear. And we have to remember that Benjamin's much-cited lines, the manner in which human sense perception is organized, the medium in which it is accomplished, is determined not only by nature, but by historical circumstances as well. Ist nicht nur natürlich, sondern auch geschichtlich bedingt, instantiated, bedingt, a word that we could come back to. Benjamin's formulation, of course, recognizes that complex social investigations into the frames of our perceptual apparatus and inquiry into its basis in human biology and psychology were not mutually exclusive. We just stated it very clearly there. But I think as a discipline, we tended to be very excited by what Benjamin said about the social construction of seeing. And if you think about the way that we then, that kind of excitement then rippled through with new strains of historical and cultural inquiry. I'm thinking of Stuart Hall and cultural studies in the 50s. We sort of were very excited to bust art history out of its endless return to the same narrow range of objects. The conditions therefore got created for an expanded field of art history, and this will be very familiar to many of you here, in the various iterations of visual studies, visual culture studies, Bildwissenschaft, as it's called in some German centres. And this is particularly a sort of story of the last 40 or so years. And it's been so fertile for so many reasons, not least the geographical and temporal expansion of our fields of study, but insisting that vision, or exploring vision, might lead to some, if not generalizable, then useful understandings of human and cultural interactions. And the Power Institute that I now have the great privilege to direct, in its creation and its theoretical underpinnings, really, and its ambitions, owes a lot to that moment. I mean, that's a sort of founding moment, not just in Europe and America, but right in here. And this event, I think, also owes a lot to that current of thought. And it's, I still feel we're fully to grapple, though, with the complexity of what it might mean. And, when I think of the various models that even in the last decade or so have been offered to understand visual culture or what it might be, ideas that are contained, for example, in very different ways and from different traditions, but people who still were brought up in visual culture, like Whitney Davis's large and difficult general theory of visual culture, whose range of conceptual apparatus and terminology tries to find all these other words for vision, like pictoriality and iconographic succession, visibilization, indiscernibility, often head-scratchingly multiplying a series of things, like as if we need to try to work out how to subdivide vision or how to try to make it sort of realizable. But then I also think of someone like Darby English, coming out of a very different tradition of visual studies, who talks about soft looking and long looking, or tries to give us new methodologies as if, in fact, what we really need is to adopt strategies of looking rather than to keep defining. But I mean, all of this growth of visual culture studies has happened in parallel with the increasing pace of image proliferation. Now, I know it's very true. Historians will hold the fact that, it's like the middle class is always rising, images are always proliferating. You could argue that, you could situate yourself in the mid-18th century, you could say the image, but I think the data is in. The data is in about the massive exponential increase in the proliferation of the image that we're now dealing with. And it's really, this is a story of the last 15 years rather than even the last 40. The need to face clearly a new age of instant diffusion and infinite malleability of digital images, new regimes of vision, as Tag or Crary might call them. And I think this has engendered a sense of both anger, crisis, or whatever we want to call it, and call to action. So I think, obviously, one of visual studies' most important figures, Nick Mirzoff, who clearly has striven consistently to try and conceptualize what vision might be, but who believes that we're in a moment of what he would call neo-visuality. And he uses that term, as you know, to describe a regime of seeing that is urgently in need of challenge. So he calls it, I will quote him, neo-visuality is a doctrine for the preservation of authority by means of permanent surveillance of all realms of life, a Gesamtkunstwerk of necropolitics. Which is a fairly inimitable phrase, but for Mirzoff, visuality in its 21st century form emerges from the prison and the plantation. It's an authoritarian, neo-colonial, racist visual apparatus that is increasingly hard to escape from. Vision is captured and violently coerced. This regime, Mirzoff says, works by classifying, separating, and aestheticizing. And thus together forms what he imagines to be the complex of visuality. Now, these words will make us worry in the academy and in the museum. Perhaps our job, the classifying we do and the ways and our aesthetic distinctions might be caught up in systems that we are not necessarily as innocent or as or even as kind of devoid of political valence as we might have thought. But I would like to say that yes, I mean I think in a way the answer to that is it's a fair cop gov. But I would also say that I think art history has, and I can't believe I'm doing this, but I'm going to go back to Wulfflin. The founding texts of art history, from its inception, belie this cliched tale of art history as simply an aestheticizing regime or as irredeemably posh. I know it's a joke that you've all heard before, but I famously remember Jeremy Hardy, the famous British comedian, who said, art history is a discipline for people who marry their cousins. Or it's a subject involving the expert eye, the completely, having regard only for sort of monetary or cultural plus value in specific ways. What we're all doing, I think, here is attempting to demonstrate, argue for, even begin to model the more capacious, I think in fact Huey called it the more promiscuous model of art history and what it might be. Wulfflin said, as every history of vision, Sehgeschichte, must lead beyond mere art, it goes without saying that differences to the eye are more than a mere question of taste. Conditioned and conditioning, they contain the basis of the whole world picture of a people. In German, it's quite beautiful, bedingend und bedingt enthalten sie die Grundlagen des ganzen Weltbildes eines Volkes. Folk is a complicated word. That is why the history of art as the doctrine of the modes of vision, and I'm continuing to quote him, can claim to be not only a fellow traveller, begleiter, accompanist in some ways, in the company of historical disciplines, but as necessary as sight itself. Notwendig wie das Gesicht. Wulfflin was, as far as I understand it, both granting the agential power of world picturing, and we'll hear more about that on Saturday, and urging us that there's no vision without the history of vision, and that for much of the world's cultural life, non-textual, material, visual history is the history. And George Kubler, of course, reinforced this many years later. Visual knowledge and visual acuity is vital to make sense of it. So that's a case that's also been made very strongly by our First Nations colleagues among us here, but also you will have heard Terra visiting Professor Gerald McMaster talk about exactly that. And across museums, universities, and the general culture, an insistence on visual knowledge and an understanding of modes of vision has led, among other things, to a variety of new understandings and a real sense that First Nations artists have a privileged role in community, self-exploration, and history. So we're going to hear a lot more of that on Friday. But we might also note that when Wulfflin uses the term Weltbild, world picture, he's literally picking up an idea that is not confined to a picture of the world that it might have been or is, but what it might be. So an active, powerful, global, and future-focused idea, which might become the conscious, artistic, and intellectual response to the dilemmas of the present. So I take some, we all went a bit wrong since Wulffen, you could argue, but there is, even in the traces of what art history was meant to be, some sense of the capaciousness and the ambition of the discipline. So even Nick Mirzoff, as he described the terrors of neo-visuality, he found it necessary to theorize a response, the right to look, something he took from the very same Derrida's response to actually in this famous essay that accompanied a rather amazing series of photographs by Marie-Françoise Blissard. The right to look, he says, is not about seeing. It begins at a personal level with the look into someone else's eyes to express friendship, solidarity, or love. That look must be mutual, each person inventing the other, or it fails. It's an interesting and slightly utopian idea or response, but its idea that it's primal brings us back to why it might be important to re-explore the psychic affective networks of visual engagement, because instead of just opposing this to cultural histories of seeing and saying, well, you're just talking about a human constant, we might be saying there's a bedrock of really important interpersonal stuff going on that we can build from to oppose the very regimes that we seem to have imposed. Okay, so I have going to stop talking now, you'll be very glad to know, and I'm going to lead into my wonderful colleagues who are going to be talking, and I'll just give them a quick introduction. But my sense is that we're going to need a lot of cooperation, a lot of sharing of insights across disparate disciplines, that very, like, sort of, to slightly paraphrase and probably take him out of context, Nick Mirzoff, like that idea that we might have a glance and exchange with each other, bond, in order to attempt a response and a meaningful answer to some of the regimes that do threaten us. And if we're to chart the mechanisms and stakes of seeing in the 21st century. So let's begin, right? In the next half an hour, you're going to, the couple of 20-minute papers you're going to hear now, you're going to hear from a scientist and an artist, and then we're all going to take that stage. I've chucked out enough provocations. I hope that you've got some questions already. I'm going to do a quick, brief introduction to our speakers, and we will run from one talk to the other without a break, and then gather all your questions for the end. So especially as Anina's speaking, if you have a question, write it down so that you can remember it when the time Trevor's finished speaking. And we will take the stage there, and we will open immediately to questions from you. I'll probably add a couple of provocations myself. But our first speaker is Professor Anina Rich, who is ARC Future Fellow and Professor in the School of Psychological Sciences at Macquarie University. And Anina's expertise is mostly focused on human sensory processing, particularly attention and its mechanisms, and on unusual information integration, like synesthesia, where you may have heard Anina's program for the ABC on synesthesia. Anina holds a very prestigious ARC Future Fellowship at the moment, the marvelous title, Dealing with Distraction. I think that's still its title. Anina's title of her talk today, though, is Our Construction of Reality, The Case of Colour. Please welcome Anina.
Whoa, feeling the pressure of starting this one off, I tell you. That was just to make sure you're all awake, which of course you are after that scintillating, and I had to concentrate quite hard, Mark, particularly because you set up an attention talk as well as a colour talk, and we made the decision that that was another whole talk. So I'm actually going to focus on the case of colour, but I'm happy to talk about attention, which is my major research area in the lab. I would like to start by acknowledging that we are on unceded Aboriginal land, that the work that I'm going to present today was conducted at the Wallumattagal campus of Macquarie University, which is land that has been a source of an area of learning and education for thousands of years, with Macquarie University being only a small part of that history. So I acknowledge the traditional custodians of the land, their elders, past, present and emerging, and I pay my respects to any First Nations people here today. So I appreciate the invitation. It's always a bit of a challenge. I'm a neuroscientist, a cognitive neuroscientist, and so I spend a lot of my time thinking about how the brain does stuff. I do teach, although not currently because I'm on my future fellowship, which is a great luxury and I'm enjoying immensely. Part of the teaching is about working out how to communicate why it's important to understand how the brain works. Why is it important to be able to quantify or measure that deeply subjective experience of perceiving the world? And so today I'm going to focus on just one illustration of that very subjective experience, and we'll look at colour as a fundamental part of vision, but it holds for all of your perception. And so I guess my challenge that I put to you today is to try and get you to question your senses, question what's coming into your brain, and question how you interpret it. So, thank you for the invitation. It is always exciting to try and link science and art. I find it really great because I get new perspectives and always learn a lot. So let's start then with this image, which really isn't a vision science thing, right? I mean, vision scientists, we like to think that we've got something, you know, some unique insights to give in understanding how we see depth and perspective and colour and form. But of course, the artists worked that out a long time ago, right? All of the cues to this amazing chalk art, which is a 2D image, represented on a 2D image that you're then representing on the 2D image of your retina, gives us this incredible perception of depth. So perhaps one can argue that artists use many of these cues and vision scientists try and help us understand why that works. The brain is essentially trying to make sense of the world around us. And art like this, I think, is a really wonderful example of, or a demonstration of the way that this happens pretty much completely involuntarily and unconsciously. That we're integrating information not just in terms of what's incoming, right? The sensory input that's coming in is not just stimulating those neurons in your the ganglion neurons in your retina and heading through to your occipital cortex at the back, but it's being interpreted constantly and predictively by what you already know about the world. This is a challenge, I think, for that perception that I see what's out there. We don't see what's out there, we see what's in here. And that means that the way that we interpret incoming information is always going to be biased by what we think we know already. And so in a society where we're getting more polarised and connections are more important than ever, and I mean real connections face to face, not perhaps through social media where that apparent connection can be so skewed and biased. Understanding that what we perceive is completely through a filter of what we already think we know can be really important in trying to build bridges, and I think acknowledging that is the first step. So I'm going to suggest that you should question your reality, because the brain makes up a lot that isn't really out there. And actually, the brain also misses a lot that really is out there. So that's the second talk on attention that I'm not going to give you today, but that Mark kind of set up in the gorilla example. So the fact that he mentioned the gorilla beforehand meant that most of you, if not all of you, will have seen it, even if that was a new video for you. But when I show my undergrads a video like that or something very similar, and if you just set it up as, I really want you to concentrate on that primary task, your awareness is massively limited by what you're attending to. Right? So there's a number of different demonstrations of that. And really the brain is combining all of this information mostly accurately, right? There's information coming from not just vision, but your other senses, to give you that conscious experience of the world. So right now you're integrating the sound of my voice and my lips moving, and that integration, which feels effortless but computationally is massive, helps you hopefully understand what I'm communicating. So extracting what's relevant from all of that massive amount of sensory information is really filtered by attention. And we're paying attention to things that are currently relevant for our goals, right? So now you see part of the problem here is that we're filtering what's coming in through what we already think we know, and then we're only going to become aware of the things that are currently relevant for our goals. So we're missing a lot of information. All right, so we'll focus primarily on the first one and really look at why we shouldn't believe necessarily that what we see is what's out there. So I call colour the ultimate illusion because it is completely in here. Colour doesn't exist in the world, right? It's a combination of reflectance of light from an object, and what doesn't get absorbed by the object gets reflected, and you've got photoreceptors in your eyes, in your retina, that then absorb those wavelengths and makes up something when you get to the brain that we call colour. So if I show you this, oh, this was supposed to be a little video, but that's all right, it's kind of annoying when it goes anyway. These different fruits and vegetables that maybe show if there's a, I don't think I have the cursor control. No, okay, that's all right. So these different wavelengths of light that are being reflected from these different fruits are obviously really important in terms of distinguishing different types of food that you might eat, directions, all sorts of things. So colour is really important in our world. And there's often an assumption that we're seeing something that exists. If we now think about that as, okay, this is reflectance of wavelengths of light, then we have a question here, which is how does the brain construct this experience? What is it that influences, and how can we use it to kind of illustrate some of the assumptions that the brain's making all the time? So we can measure the wavelengths of light that's reflected by an object and try and look at that from an objective point of view. But the problem is that sometimes the same wavelengths of light are reflected from an object and we get a perception of a different colour, or we get a perception of the same colour, but when you measure it, the wavelengths of light are different, right? So this is a really clear demonstration that what we see in the world is not actually what exists. Christian, could we swap to the website? Oh. Okay, it's all right, we're just opening the website, and then you'll see. It's just easier to show this in a dynamic setting, that's all. Okay. Are we good? Thank you. So here's just an example. So I've got that Rubik's Cube on the slide, but you can't really see what I'm trying to illustrate, which is that the wavelengths of light that are reflected from this square here and this square here are actually the same. But the perception, I expect, unless you're colourblind, which is about quite a proportion of the population, so you might see something different, but effectively our visual system corrects for the fact that this is apparently in shadow. And because I opened the website because now I can show you, right? So as you move into the shadow, the perceived colour changes. Can we go back to the slides, please? By the way, the link is on the slides, and if you want to go and play with some cool illusions, that website's really useful for doing that. There's a whole lot of these illustrations of how what we're seeing is actually not what's out there. Okay. Are we ready? Okay. So you might remember the dress. This was an image that went viral on the internet a number of years ago. And it caused a furore because people's perception was so different. Some people, put your hand up if you see this as blue-black. Okay. What about people who see it as white and gold? Oh, I'm among those ones, by the way, right? If you see this as white and gold, it's very hard to understand how someone could possibly see it as blue-black, right? I don't see it as blue-black. I can't make myself, I can't use my attention to switch it. I can't make myself see what you see, right? And the reason that this image, particularly worked is because the lighting cues are unusually ambiguous in the photo. So it's essentially an illustration of your brain's unconscious correction for illumination. So those of you who are seeing it as blue-black, your brain has assumed that there's warm illumination. Whereas those of us who see it as white and gold, my brain's correcting in a different way. And it's correcting based on assumptions that my brain just automatically is making. Okay? So the reason that these sort of things work, these sort of mechanisms, reflect something called colour constancy, which many of you as artists would know all about. In a sense, it leads to those different experiences with the dress, because our brains have to use the clues around us to correct for changes in illumination. And if this didn't happen, then you walk under a tree and all of a sudden the colour of everything would change, right? We need to have some constancy of the world around us. If we didn't have it, as you walk through different shadows, even as I move my hands, everything would appear to change. All right, so when we talked about what we were going to kind of cover today, Mark asked me to make sure that I included some cool cognitive neuroscience methods, and that's exciting for me because I think it's always nice to share what the ways that we can study the brain. And so I thought that I would actually structure it in terms of giving you a sense of different types of colour representation in the brain. So we've just been talking about what people might call real colour perception, right? I've got quotes around it because I've just told you that it's not real at all, and in the sense that it doesn't exist out there. Okay, but let's accept that we're going to call it real colour perception. Essentially what I mean is colour based on wavelengths of light, relative wavelengths of light, taking into account illumination. Typical scientist, I can't avoid giving you a caveat, but we're looking at reflectance of relative wavelengths of light. And so that might be what you're seeing up there with the lemon. We're also going to look at a really clear illustration that what you know about the world is generated involuntarily when you perceive objects that might trigger that. So in this case we call it implied colour, but it's really an illustration about the knowledge that we have about typical colours. So our experience in the world has led us to know that grayscale image is of a strawberry, and strawberries are usually red, certainly when they're ripe and ready to eat, right? And so actually what I'm going to show you is that when we see a grayscale image like that, your brain automatically activates some sort of representation of colour. And in the final one, Mark also mentioned this, a lot of my work over the years has been on synesthesia, which is a phenomenon where you have an involuntary experience, often of colour, to an achromatic stimulus, or a stimulus that doesn't usually give a particular sensory event. So sounds can give colours, letters are coloured, smells can be coloured. There's a whole lot of different type of experiences in synesthesia. So I'll quickly show you some data from people who experience synesthetic colours in response to letters and show you how this all fits together. Okay, so how could we do that? Well, we use the National Imaging Facility at Macquarie University, magnetoencephalography setup. It's a big fancy word. I would say MEG so I don't trip myself up. Essentially what MEG does is it allows us to measure the teeny tiny magnetic fields given off by populations of your brain cells all firing together. So when your neurons are talking to each other, there's an electrical current, the action potentials firing between the neurons, and every electrical current gives off a perpendicular magnetic current. And using this fancy machine with the helium-cooled sensors that are incredibly sensitive, and a massive room that's very expensive because it blocks out the magnetic field of everything else, we can get a measure of what's happening in your brain, a direct measure of the neural activity. Only if lots of neurons are doing the same thing, and there's a whole lot of limitations, but it's pretty cool because we can measure the teeny tiny magnetic signals given off by a human doing a task, and use that to try and understand what's happening in the brain when you're perceiving colour. Now, we're also using a relatively new methodology for analysing these data. And that is that we train a computer algorithm. So as you'll hear later on, computer vision is a whole area. Then, of course, we've got the machine learning algorithms, which, in various forms have been called AI. Here I'm using something much simpler, just a linear classifier. But essentially what we're doing is we're able to train a computer on what it looks like. So if I show you lots of things that are red and I show you lots of things that are green, in each case you're going to have a pattern of brain activity while you're perceiving that, right? And so I can present this to a computer algorithm and train it basically to say, okay, well, at this first time point, the brain pattern at each sensor looks like this for a red trial and this for a green trial. Here's another red trial, here's another green trial. Of course, we don't just have two sensors, right? We have in this case, 164, I think. And so we can get this representation of what the brain pattern looks like when you're seeing different things, in this case colour, okay? But we can apply it to a whole lot of other areas. And essentially all we're looking for is some sort of boundary between them that can distinguish those two clouds of dots. And you might not see much at time one, very early on after a stimulus has been presented. But as time goes on, you see a greater separation. And so it's a greater dissimilarity of the brain patterns as somebody seeing red or green in this case, right? So then we take new data from that participant. We have to see, did it work? Well, if the boundary that you've developed can distinguish red and green reliably, then we know that that pattern of activation has some information about colour, right? And so we can start to look at how these perceptual processes unfold over time, how cognitive processes, so we're also using it in studying attention, but it really gives you a sense of the information that's present in the brain for these incredibly subjective experiences. I can never tell when we describe colour whether or not we're seeing the same thing. I can't use a fancy machine to tell that either, but at least what we can do is we can say, well, here's a neural representation. Here's a pattern of activation, measurable at the scalp, that I can then say, okay, well, this is what it looks like in your brain when you're seeing colour, right? And then we can say, okay, well, at some point, do I have a cursor? Yep. So at some point, maybe at time point 1, it's not above chance, but at some point we can see that there is information about colour in the display, right? So that's when we would use it. All right, so now we have this method, we can use it to try and understand something about that subjective experience of colour. So here's an example, and these studies are all part of an ex-PhD student's work, Lena Teichmann, and I'll show you her at the end. She's now doing a postdoc at the National Institutes of Health in the US. So we can train our classifier on our red versus green, and if we do that, what we see is, I did promise Mark that I would present data. I hope that's okay. I get excited when I see data. Hopefully you do too. So here we have the time relative to when the stimulus was shown. And on the y-axis, we've now got this decoding. How good the classifier is at saying this is the brain activation of someone seeing red, right, versus green. And so what you see is that before the stimulus comes on, there's nothing. For the first 50 milliseconds or so, there's nothing. But then we start to see, by 80 milliseconds, we can actually have our computer algorithm telling from the brain pattern whether or not someone was seeing red or green. Okay? So that means that we can reliably say, I can decode whether or not you were viewing red versus green. Can't say anything about the qualia of what that experience was like, but I can at least say that there's something in your brain that's representing that I can pick up. Okay, so given that we now have that, and we have that time course, we can use that to try and understand how does seeing real colour, wavelengths of light colour, relate to the type of other experiences of colour that I sort of highlighted at the start, the implied colour of objects or the synesthetic colours. So we now have like this objective index of kind of way of saying, is what's happening in the brain similar between these types of reported colour experiences? So in the implied colour study, we again trained on these real colours, right? So the classifier is the same. The computer algorithm is trained on us seeing the real colours, but now we're testing on brain activation when people are seeing objects that are normally red or objects that are normally green. If there's some overlap in the neural activation when you're retrieving object colour knowledge like that, that's in any way similar to when you're seeing real colour, the classifier should work above chance. It might be only just above chance because there's a huge amount of difference between this. But if it's reliably above chance, then we know that there is an overlap in that neural pattern. So I have to show you the data in a slightly different way for this because it's not at the same time. And that makes sense. I flash up a stimulus, within 80 milliseconds your brain is processing that information in the visual cortex and it starts to go through the hierarchy, right? When you see an object, you first have to process that to the level of understanding what that object is. So that's going to take time. But what we do see is that there is a similarity. So these graphs are a little bit complicated, but essentially all it's doing is this is the training on the real colours, right? So when I train, it's about 100 milliseconds or 150 milliseconds after stimulus onset, and then I test it on the objects at about 200 milliseconds, we have an overlap in the neural activation. So that basically gives us objective evidence that when you see a grayscaled object, you are retrieving a colour experience or a colour representation. It might not get to the level of awareness, right? So it might not be an experience, but it's the same. It's not the same as low-level colour. It's a bit later, but it's there. There's a neural pattern. Okay, so what then about these people who report seeing a colour when I show them letters and numbers that for the rest of us have no colour in the display? So for synesthetes, these different numbers and letters will have vivid, consistent and very specific experiences that they evoke. So for each synesthete, what we did was we selected stimuli that for them evoke red or green, right? And then in the same way as we did with the implied colour, we can train our classifier again on the real colour. But now we're testing on, okay, I showed them a 6, which for them is red. There's no red in the display. What does the neural pattern show? Okay, can we see any objective evidence of these subjective reports? So again, we're training on the real colour, and we're testing, but now we're testing on letters and numbers, neural activity from people seeing letters and numbers that are either synesthetically red or synesthetically green. And again, I'm going to show you this time generalisation graph because we need to train on all the different points in the colour perception to see whether or not there's something there when you're seeing a synesthetic colour. And what you can see here is that it's much more dispersed than for implied colour, which makes sense because there's a lot of individual variability in synesthesia and indeed in perception in general, right? But the more unusual the experience, the more variability you tend to get between people. But this, even though it's only 52%, right? The classifier got it right 52%. That doesn't seem anything to write home about, but it's reliable and it's across people. And so what that means is that we now have an objective validation of people's reports. And so for synesthetes, you know, many of whom have been told, oh, you're making it up, or you're just kind of thinking that those things go together like deliberately, this was actually a really exciting finding. Because what it is it's saying, no, straight from their brains, we can see that the pattern of activation is indeed overlapping with what it is when they're experiencing so-called real colour, okay? For me, it was exciting because now we can start to say that colour representation overlaps with what we all experience about 200 milliseconds in, right? So again, you can't get at the qualia with this, but it kind of gives us a unique way of getting an insight into these levels of colour experience. So I've sort of shown you how these methods can help us look at colour, but we can apply these in a whole lot of different ways. Obviously, often when these things are reported in the media, it gets a bit beaten up, so I wouldn't call it mind reading, although it has been called mind reading. I wouldn't say that, you know, we're going to uncover all the secrets of the brain using these methods, but I do think that converging evidence from healthy people, from patients who have experienced brain damage, from people, you know, doing deep thought and introspecting, from art, if we bring that all together, then we get a better understanding of how the brain is putting together this information. So returning then to where we started, our perception is derived and constructed. And essentially what we're doing is the brain's making an informed guess about what's going on. If we come with huge biases, then our perception of what's going on is going to be very different from a person who has a different set of preconceptions about the world. And so understanding that our knowledge of the world shapes what we see and what we perceive, I think gives us the opportunity to think outside our own biases, to try and connect and say, use language to try and understand how someone else's perspective might be quite different. And I hope it was useful to see that colour can provide a unique illustration of this. And I'll end by thanking Dr. Lena Teichmann and my other collaborators on these projects and my wonderful lab. So thank you very much.
Thank you so much, Anina. And I'm going to move straight on to Trevor, and then we'll all get together to answer your questions after Trevor's talk. So our second speaker is Trevor Paglin, and Trevor is an artist with an MFA from Chicago, a geographer with a PhD from Berkeley, and an ambitious photographic and installation artist known to you many here. Among his many major shows and exhibitions, the recent mid-career retrospective Sights Unseen, which I think is a useful cue for some of the topics he's going to cover, at the Smithsonian, and then it went to the SF Museum of Contemporary Art. And we also know that Trevor is the recipient of the rare and coveted MacArthur Foundation Fellowship, and his long interest combines artistic practice with a real thought about how certain human geographies work, how surveillance works, how human-computer interfaces work, and what the human is to do in their current perceptual environment. So his paper today, I hope, is entitled Neural Images, and I would love you to join me in welcoming Trevor Paglin.
Thank you guys so much. I'm so happy to be here, and I must confess, jet lag is a hell of a thing here, man. so I'm going to do my best to try to keep up. And I feel like I'm going to say point out a lot of the same things that Anina was looking at, but kind of using a different language maybe, and looking at some different examples of that. Can we go right to my slides, or does it just go forward? Oh, here we are. Oh, you have an older version of this presentation. All right, hopefully it'll be fine. So, first, let us consider the shrimp. I assume everybody's familiar with this kind of image, the Pope with the puffy jacket, the wish fulfillment Trump. So these are obviously, as you know, these are well-known AI-generated images, and they kind of work because of the really kind of sly semiotic contradictions contained within them, the wish fulfillments, the quasi-surrealistic absurdities. And what I want to talk about today is the theory of vision that created the ability to make images like that. Because underlying these kinds of images is a theory of how images work that has nothing to do with semiotics, that has nothing to do with wish fulfillment, that has nothing to do with surrealism. And so how do we try to bridge that gulf? This is another way in which what the stimulus that we're perceiving is wildly at odds with how it was created. And I want to suggest to you that the reason that we can read images like this has to do with the fact that we've learned to teach computers how to make us hallucinate. And so I want to talk today about how computers do that. And our story is going to start in 1959 at Johns Hopkins University. And what was going on there is that two early neuroscientists in 1959, David Hubel and Torsten Wiesel, they started doing things to cats. And I'm going to show a video next that is, I should give a trigger warning, because they did not do nice things to cats, and I'm going to show some of that, and you might not want to watch it. So giving you some fair warning here. But the question that they wanted to answer was this: how do cats, and by extension humans, see? And at that time, nobody knew what the relationship was between photons coming into our eyeballs and the meanings that we derive from those visual stimuli. In other words, do we perceive objects as fully formed wholes? Does the brain create a three-dimensional model of an object and then try to fit images onto that model? Or does vision do something entirely different? And so what these guys decided to do was to crack open the skull of a cat, attach electrodes to the interior of its brain, and then showing the cat lots and lots of slides, different kinds of images. And the idea was to see what kinds of neurons fired with different images. Now, what they imagined that the absolutely most exciting image that a cat could possibly see would be a fish. This is an AI-generated fish, by the way. And they imagined the cat's neurons lighting up with excitement, but instead, nothing happened. What's going on? Why aren't these neurons, why is this cat excited about this fish? And over time, what they realized is they were using slide machines back then. They realized that when they changed the slide, the motion of the edge of the slide from one slide to the next would make the cat's neurons start firing like crazy. And the cat was reacting to the movement of the edges. And so the conclusion that they arrived at many, many conclusions, but one of the conclusions they came to was that the neurons in the visual areas of the brain were firing that had some relationship to these edges. And this might seem like a trivial insight now, but this is a very huge insight at that time, and probably more than anything else, created the basis for future computer vision and AI research with regards to images. This was a huge clue to unlocking the mystery of vision. This sort of research was taken up by other people. In the early 1970s, a researcher named Colin Blakemore took up this tradition of torturing kittens in order to divine the mysteries of vision. And again, I'm going to show you a very triggering video, so you have been warned. You can close your eyes and your ears even if you want to. Do we have audio? There's audio to this video. Can you please play the audio? Okay, looks not like that's not happening. So the idea here was that they would raise kittens in complete darkness. And they would only take the kitten out of complete darkness for a few minutes every day. And when they did that, they would put the kitten into these containers where the kitten could only see horizontal lines. And they put a neck shield around the kitten so they couldn't look at itself even. So they would raise these kittens in such a way that they only grew up ever seeing horizontal lines. And then when they took the kitten out finally, after a number of months, they put it in a normal environment and tried to show it different lines, horizontal lines and vertical lines. And as you can see here, the cat's seeing a horizontal line and it can see it. It's reacting to that. And then they changed it around and showed the cat vertical moving lines. And this was, again, a cat that was raised in an environment where it only ever saw horizontal lines, and it literally could not see the vertical stick that was moving around. So what was the implication of this? Well, these experiments implied that vision works by building up representations from very crude building blocks. We don't just see a fish, we subconsciously build up the idea of a fish from edges, gradients, and other very basic shapes that we perceive. And we can put those basic shapes together to get concepts like objects, things that we perceive as objects. And so the theory here is that images work in ways that are analogous to words. Each word is, of course, made up of letters, and letters are the basic building blocks of language, and they can be rearranged in different ways to produce different words and subsequently different concepts. And this work implied that something similar happens when we perceive an image, that our brain perceives this collection of basic shapes in a particular pattern, akin to a particular pattern of letters that form a particular word. So when we see an image, our brains are actually conducting a kind of magic trick. When we perceive an object like an orange or an apple or a face, what we're really seeing is a collection of simple shapes that are activating particular neurons in our visual cortex to produce a particular pattern, and that pattern corresponds to something that we might call a face or an apple or a strawberry or what have you. This picture looks nothing like a face, right? This is a crude drawing, and yet we all see a face in these lines. So our minds are hallucinating the idea of a face, even though we're looking at something that looks nothing like one. And this is why, of course, we see faces all over the place. We see pictures of sheep in clouds. We see the face of Jesus in slices of toast. And this has a lot of implications. It implies that everything that we can perceive can be broken down into these combinations of shapes. And furthermore, it implies that every object in the universe can be represented by a particular combination of these basic shapes, just as every word in any language can be represented by a series of letters. So, in the same way that you can create a word from a small collections of letters, the theory went from a collection of basic shapes, you can create an image of anything. Now, this theory of vision that Hubel, Wiesel, Blakemore, and others outlined had a lot of implications. And one of the implications was that vision could potentially be quantified. If all images and all objects can be broken down into component parts, and if you could represent those component parts digitally, then you could theoretically create computer vision algorithms that replicated that process. You could build computers to see the world. Now, this insight had other implications as well, which is one, if you could create a database with pictures of all the objects in the universe, you could use computers to break down all of those images into their component parts, and you could discover the kind of genome of all images. And if you knew the visual DNA of every object, the primitive shapes that put it together into an image, you could train a computer to recognize any object in the universe. And fast forward to 2009, a collection of researchers at Princeton and Stanford decided to do just this, but we will get to that in a moment. I'm going to do a little side quest here. In the early 1990s, the American military and the National Institute of Standards revisited attempts to invent facial recognition that had been going on since the 1960s. The military wanted facial recognition to exist, and so they set out to make it so. The problem was, where do you get a bunch of images? There's no Instagram, no Facebook. They came up with two solutions. One was a database called Ferret, which was made by taking pictures of people who mostly worked at military bases and digitizing those images and creating them as a database that computer science researchers could use. So they had this. It was the National Institute of Standards data set to use for facial recognition research. But there's another place that even in the early 1990s, you could get a bunch of pictures of people's faces. The second major database came from the faces of prisoners. So this is a look at some of the early types of data sets that were already kicking around in the world of computer vision before the place that we will re-pick up the thread that we started earlier. So to go back to this idea, this dream of creating computer vision systems that could see everything in the universe, already we knew you would need to have a database that had all of the objects in the universe, that database would need to be labeled, and so you would need this massive, massive training set. This was impossible to do in the 1970s or 1980s, but when we fast forward to 2009, this started to become possible. And in 2009, a team at Stanford started to make such a database, and they called it ImageNet, and it is the most widely used data set in computer vision research. And it's massive, it's intricate, it's incredible. It's a kind of almost like, I don't even know what the right adjective would be, but it's something akin to pyramids or something. It's massive. There's about 1,478 images of strawberries, 932 pictures of strawberry ice cream, 604 pictures of strawberry daiquiris. It goes on and on and on. There's apples, apple butter, apple fritters, apple dumplings, apple jelly, apple juice, apple pie, etc., etc., etc. And over the next few years, these researchers at Stanford and others in the field, like Alex Krichevsky working under Jeff Hinton at the University of Toronto, they realized that you could use neural networks to do this thing that Blake Moore and all's experiments imply, that you could use neural networks indeed to break down all of these images into their component parts and look for patterns in those parts. And when you did that, you could build computers that could recognize objects. I'll show you a dramatically simplified way that this can be done. Let's say you want to build a neural network to recognize objects in your kitchen. You have to start first with a database of all the examples of all the things in your kitchen. Fork, knife, plate, spoon, banana, what have you. And then what you do is you have to give that neural network a bunch of examples of the things that you want to be able to see. So you give it thousands of pictures of oranges, thousands of pictures of apples, spoons, what have you, etc. And the machine learning model is going to ingest all of those. And then what it does, it breaks all of these images down into these basic shapes and maps those across kind of what are called the deep layers in the network. And then what it does is, once it's done that, what it will do is you can show it an image that it's never seen before. We'll say, okay, here's an image. And the model will say, okay, well, we have some lines, we have some edges, we have some ellipses, we have some gradients. There's not a lot of color information, although I know that's a contested thing, but it's a little bit different in digital images because it can be quantified. And it says, if you have this collection of basic shapes, and this is the possible number of objects that it could be, then you are probably going to be a spoon. An image like this is going to have a lot of the similar basic shapes to a spoon, but it's not going to have that ellipse at the end. It's going to have some kind of spiky thing, so it's probably a fork. Bananas, completely different. Arcs, yellow gradients, and what have you. You're a banana. When you do everything right, you can do stuff like this. Unfortunately, they got extremely proud of themselves and imagined that this sort of technique could be put to all sorts of, used in all sorts of domains where it is wholly inappropriate. Now, in the last few years, we've seen another shift, another variation on this happen. Remember how you can you can build machine learning models to recognize images? Well, you can also use those models to simply synthesize images. And what you do is you essentially run the system backwards. So instead of looking for these basic shapes, you're synthesizing them. And you're synthesizing those basic shapes together into a particular pattern that meets the criteria of the pattern that you're looking for. And this is an early example of this kind of thing that we built in my studio in, I think, 2016. And this is the kind of thing that you can do these days with it. So, where are we at now? Well, let's go back and let's remember these cats. The researchers didn't care about the meaning of images. They cared about how different stimulus activated different patterns in the brain. And remember that this observation between stimulus and activated neurons was is what underpins contemporary neural networks. So this implies a way of thinking about images. So like, let's forget semiotics. They don't care. That's not what's going on here. An image is, in this theory, something that excites a particular pattern of neurons, bypassing language, bypassing concepts, and operating entirely preconsciously. So there's a pretty crazy metaphysical claim implicit in this theory of vision, that reality, whatever that is not what we are seeing. What we are seeing is a particular pattern of neurons firing in our brain, to echo a lot of the points that you were making. So in other words, when we see an image of a thing, we're really seeing a hallucination that our brain is making for us based on a particular pattern of external stimulus. So this is a pretty good illustration of what's going on, but the monkey, strictly speaking, isn't seeing the action. What the monkey is seeing is the patterns in its own brain activating, which is inducing the monkey to see the action. And of course, this was a very memeable image. So, in this paradigm of like neural media, the paradigm is not about representing. It's not about, what it is about is trying to figure out how different media produce specific neural responses, whether it is an image of an orange, but those kind of responses could be other things like anger or outrage or anxiety or titillation or what have you. And we can think about recommendation algorithms or algorithmic feeds optimizing for these sorts of things, and we can already see that this kind of thing is breaking our brains. And I want to propose to you that this is going to get a lot weirder. When we look at some of the research being done now, using machine learning and generative AI to evolve images, or more precisely to evolve stimulus that maximally stimulate different brain patterns in monkeys. Right? So like for example, taking the color experiments that you were showing, Anina, and then using machine learning to generate images that would maximally stimulate those different kinds of patterns, kind of taking them up to 11, the kind of image equivalent of a Dorito, perhaps. And I think that this is evolving into a very weird media landscape that we might find ourselves increasingly inhabiting. And I will expand on that in the talk tomorrow. Thank you guys so much.
I'm just going to a few minutes while we sit ourselves down and set mics up. Does this work? That works, right? So I'm aware of the combined brain power of this room and inquisitive nature of this room. So I'm not going to add any further gloss. I'm going to ask directly for some questions that you might have for Anina and Trevor. And what I'm going to do is ask you to put your hand up. And when I see you and I point to you, a gentleman or a lady with a mic is going to come and find you. And only then, when it's really close like this, speak into it. And because that's an uncomfortable thing, maybe you might like to keep your question nice and brief, or at least brief.
Am I allowed to raise my hand?
Yes, you are, of course. And if you'd like to kick us off, I'd be happy. But I just, why don't you? Trevor, raise your hand.
Yeah, okay. I have so many different questions, but there was a few moments that you said something that I thought was quite remarkable that I wanted to see if you want to pack out for us. If I understood you correctly, when you're talking about the black and white strawberries, you mentioned that some of the neural patterns that you saw activating did not rise to the level of experienced perception. And so that implied a really interesting gap, if I understood what you were saying correctly. And I wanted to see if you want to build on that a little bit more, because that implies that, there is even something else going on between,
So here's a scientific caveat for you. What I said was I don't know whether or not it's reached the level of experience. So there are behavioural studies where you show someone a grayscale image or an image that's, say, a banana, but it's slightly off grey, and you ask people to adjust it to make it grey. And what you see is that, well, at least some of the studies, this is one of those ones that is a little bit hard to replicate, that people tend to adjust it towards the blue side, which is the opponent colour for yellow. Yeah. So what that suggests is that there is some sort of experience, or at least activation, which I think we've shown that there is a neural activation. Whether or not that is an experience is a question that I can't answer from that. But these data suggest that you certainly are biased towards making something more blue, as if you've got some experience of yellow that you're balancing out to make it grey. Right. So, yeah, I would say that we can't tell whether there's an experience. And there might be something else going on there, right? So for synesthetes, for example, they describe an experience of a colour. For mirror touch synesthetes, they describe feeling when someone's touched, right? For all of us, when we see someone being touched, if I've got you in, say, an MRI scanner where we can look at changes in blood flow in different regions of the brain, then there's evidence that suggests that you get activation in somatosensory regions. So regions of the brain that are processing tactile information. But for most of us, that's not an experience, right? You might, unless it's something really gruesome, like I'm a bad parent, I took my kids to see Deadpool and Wolverine. And there's a scene there where someone's got her fingers inside someone's head and you can see it bulging in the skin. There's a very visceral response that everybody probably has to that, which synesthetes who have mirror touch synesthesia report those sort of experiences when they just see usual, not so intense touch. So what that suggests is that what happens in our brains when we're perceiving, either someone being touched or these grayscale objects that are really strongly associated with colour, is that we are activating some sort of sub-threshold representation that for some people trips over into an experience, right? And we don't know what makes that distinction. Does that make sense?
Yeah, totally. Super.
That's kind of.
So we have lots of questions. I saw Huey first, so maybe I'm going to go to you, Huey. But then a lady 4 rows up here on the right, and then a gentleman. Keep that hand up, and I'll come to you afterwards. Okay, so.
Thank you both for those really fascinating, incredibly rich presentations. I'm really interested in maybe hearing you talk about the limits of how we can theorize the visual in terms of both individuation and speciation, right? So, Anina, you were sort of speaking about that sort of difference between that black and gold and, or the white and gold and the black and blue perception, and then talking about cats. I wonder, is cat vision the same as human vision? So how do we understand the sort of gaps on both the species level and the individual level, and how they force us to think about the contingencies of visual theory?
I mean, I can speak, so I should preface the answer by saying, like, that theory of vision that I showed today, I don't think is good. I think it's terrible, right? And so I think it's a theory of vision that emerges out of extremely specific circumstances, and those circumstances are isolating a kitten in a lab and torturing it, right? So that's where that emerges from, and I think we can quibble about to what extent that theory moves outside of that specific space, because obviously, it does, but at the same time, that is the foundation on which it is built. So your question is the stuff that deserves a book, at least, because there's so many different aspects to it, right? In the sense that this theory of vision ignores things like memory, it ignores history, it ignores environment, it ignores like other sensory kind of stimulus. So it throws away so much stuff that we know is relevant. We also know, as you've kind of pointed out, that even to be thinking about something while you're looking at a particular image will literally change the way that you see that image, not metaphorically, literally. Same thing happens with sounds and that sort of thing. So there's another very real, hard, dead end in terms of how far that theory of vision will go. And then of course you get into the whole universe of what does it mean to quantify social concepts like divorced man or race or whatever it is, right? So you have I'll leave it there, but yes.
And can you comment on human versus other forms of animal vision, or because we know that there are different, if you're a peregrine falcon, you don't see like a human, right?
Obviously, there's a number of differences that evolution's brought to, really hone in, for example, that the falcon, very, very finely tuned motion detection, right? But we also have actually quite good motion detection, and that's evolutionarily important. So if I'm foraging in the bush, I want to be able to focus my attention primarily on the berries that I'm looking for and use my colour vision effectively to find the ripe ones, but I can't be completely oblivious of my surroundings, or the tiger that's in the grass is going to eat me, right? So the peripheral detection of motion for human vision is also pretty good, and that tends to drive your attention, right? So my attention is focused on my berries, but then if there's a motion in the periphery, that will capture my attention regardless of what I'm doing. So I think it does depend on how far back you go in the evolutionary tree. I think in general, I would say that a lot of the things from the cats, for example, that were really fundamental in our understanding of how some of the aspects of visual vision and visual cortex develop are still fundamental. So while I agree with you that the basic shapes idea doesn't hold because it doesn't take into account all of these predictions that we know we're making about the world and how that shapes what we interpret, the fact that experience drives V1 development is absolutely holds, right? And if we don't have those visual experiences, then we won't develop what we think of as normal vision.
Yeah. My point was that computer vision gets stopped at a certain place.
Yes, I'll move on to...
Actually, that's exactly where I wanted to come in. Thanks for a fantastic talk, Trevor. I really enjoyed the kind of genealogy back to the kind of neuroscience nightmare. But I guess this is a really interesting thing, which is that, there has been neuroscience since as well, and a lot of which has disputed that kind of paradigm of vision, and has basically said, well, it's a lot more complicated, and actually we don't know what's going on half the time. Why is it that computer vision can't keep up?
Because it has to quantify something.
Yeah, but so what are the knowledge politics at stake? And I think you were starting to draw that out, particularly with the kind of platform assemblages around databases, etc. I know that's really part of your work as well. I just wondered if you could talk a little bit more about that kind of the politics invested in that quantification and the assemblages around that.
Yeah,
Sorry, that's huge. That's book two.
Yeah, so that's another massive question, but one very well understood. So you have this basic requirement with computers, which is that things have to be quantifiable, right? So you've already created an incredibly narrow bracketing, right? In longer versions of this argument, some of which that me and Kate Crawford have developed together, the claim that we make is like, actually, this is all crap. Computer vision is not about recognizing objects. It's ultimately about making money, right? So then you think about what kinds of things in the world can you train a computer to see or recognize that will be profitable to you, right? And that could be something as simple as in a kind of quality assurance environment in a factory, making sure that the widgets all look correct. Or we can go all the way over to the other side of the spectrum and see, like, maybe it's a camera in your car that is watching you drive, and it's paying attention to whether your eyes are fixed on the road and whether you're eating or texting while you're driving, and then sending that information to insurance companies, right? And that is still a kind of quantifiable thing to be able to observe with the camera, and it kind of does go then very smoothly into a kind of securitization is the wrong word, but the kind of creating a kind of invasion of capital into moments of everyday life that is facilitated through those kinds of technologies. So that's a longer answer, I guess, but it can go much longer than that as well.
There was a question at the back, I believe. Can you re-raise your hand so we can locate you? Thank you.
I'm wondering if we can break open the black box of neuro patterns. I think when we talk about it, especially in relation to computer vision, we all kind of imagine that our brains are like little computers with transistors all the way down, or circuits. But I think there's some other stuff going on at a chemical and material and electrical level. I'm wondering if you can clue us in on what we know and what we don't know.
What I was showing are neural patterns detected by these sensors at the scalp that really can only detect magnetic fields given off by electrical activity of like hundreds, if not thousands, of neurons. What Trevor was showing of those cats, and also the monkey work, they can do single cell recordings, right? There are lots of ethical implications about using animals in that way. I have consenting, awake, behaving humans who I'm not like doing the single cell recording in. But when you have that information, that does, the information that we've got from such pretty awful animal research has been fundamental in increasing the understanding of those mechanics of what's going on. So how brain cells talk to each other at an individual level, the neurotransmitters that are released. You're right, it's not even close. What I'm showing is not even close to the complexity of what's going on, right? We're trying to make inferences based on a measure at the scalp of something that's happening somewhere in the brain. And the method that I was showing you, I didn't show you anything about where I thought it was coming from because it's not the best method for that. The methods that we have for saying where in the brain something's happening, like fMRI, functional magnetic resonance imaging, trace blood flow. So they're much slower than cognition and perception. And so what you end up with is you've got the where but not the when. And so some of the computational methods that we're doing are trying to bring together the where and the when. But even with all of that, we're at the macro level. Patient work is even more macro because it's a natural experiment, if you like, right? You can't control where the lesion is, and usually if it's something like a stroke, you're losing a massive part of the brain. So we've got even less there. The single cell recording from monkeys can give you the micro level of like how an individual neuron might be behaving, and maybe like you can get a population of neurons if you've got lots of single electrodes, but then we lose the macro level. And we can't ask a monkey what they're seeing, although there was some pretty amazing research at the Vision Sciences conference in May from the Afraz's group, where they're actually using the generative AI to basically regenerate what the monkey is seeing. Yeah. Like it's kind of mind-blowing. But that aside, so the answer is I actually can't. All I can say is absolutely. It is so complicated. And then there's the question of how does all of that emerge into what you experience, right? And we can quantify it and objectify it as much as we like. In the end, it comes down to what's your experience. And we're really introspection is really not a very good tool for that, right? It's not reliable, and it's kind of shaped by how we describe it, and we don't have a good way of communicating it. So there are so many different levels of it. One of the things that I would say is that we can link these neural patterns to behaviour, and I think that's part of a big sort of push in my lab is we're using these methods, but we're also trying to say how does what we see in those neural patterns relate to, for example, whether or not you got a task correct or not. So can we see evidence about a stimulus in your neural pattern that's stronger when you then got the task correct versus not? And those sort of links, they're still indirect, but it allows us to say that the patterns are something that the brain might be using. Because it's also possible it's completely epiphenomenal and I'm studying nonsense, right? Or something that emerges because something else important's happening. And so by being able to link it to behaviour, I think that gets us a step further towards understanding the processes. And there are very clever people looking at how we can measure things like the neurotransmitter levels in awake behaving humans, using like spectroscopy and that sort of thing, and now linking that with cognition. So for instance, getting someone to do a task and trying to track the concentration of GABA in the occipital cortex, for example. But it's hugely complicated.
Thank you. There are a couple more questions. Yeah, so I'll come to you. Lady here about five in from the middle section, and then I'll come to you, Donna. I think you may have had your hand up first. So could you raise your hand so we can see it. Sorry, the mic folk need to see you.
Hello, thank you so much for your presentations. You'll have to forgive me if the answer is very obvious because I'm not a science person. But in my own field of literary and visual studies, there have been efforts over the last few decades to reckon with the incredible histories of inequality and violence with which we've come to understand hierarchies of value, what makes a canon of literature, what makes a canon of art. So I was just wondering if there have been similar efforts in science or computer studies to acknowledge and reckon the kinds of studies that, Trevor, you were talking about, these kinds of histories that may not be so palatable.
I'm an artist.
I think it's, yeah, look, I think it absolutely is something that if it doesn't feature in every field, it should. So the sort of most obvious link that I can think of there is in the types of training materials that are going into these massive AI, degenerative AI procedures. So if you put in cognitive neuroscientist, you don't get a woman, right? If you put in scientist in general, you get a white man in a lab coat, right? And if you look at the training data that's feeding into these models, it's what's on the internet. And so what's on the internet is reinforcing stereotypes. One of I think the really interesting is you said before that that we literally perceive differently an image, right? Depending on what we know or believe. And so our brains are actually also exposed to those same stereotypes that those generative models are. And one of the problems with that is that then from a very early age we're exposed to these stereotypes of race, of gender, and those then shape our perception of what's around us. So, you know, in attention research, for example, this is called various things. I call it working memory-driven attentional capture, which is not very helpful, but I think it's also called like Badenhofen. My German is much poorer than yours. Phenomenon where basically it's essentially that finding that when you're thinking about something, you then see it all around you, right? You're thinking about buying a new car, all of a sudden the type of model that you were thinking of seems to be much more frequent. And it's a combination of a couple of different types of illusions, the frequency illusion and confirmation bias, which is that we seek out information that confirms what we already believe. And we don't tend to see the information that challenges what we already believe. So from an early age, we're getting exposed to these stereotypes that then shapes what we're noticing in our environment. And so you don't tend to notice the things that are outside those stereotypes, which then is like this circular notion. So, you know, I think it's actually a big responsibility when now people are using AI to generate things to look at what are the data that are being used to train those models. But it's also the case in the science that we do. So if we are always testing undergraduates, right, that's not representing the whole population. And we need to think about how generalisable is our science. Now, in the case of my stuff, most of the time we're looking at things that are fairly basic mechanisms, right? Contrast sensitivity is unlikely to be influenced by socioeconomic background or ethnicity, for example. But there's a whole lot of science that absolutely is studying things that would be biased by that. And if we don't ensure that our data collection is equitable, that our research design is co-designed actually, particularly when you're looking at, say, First Nations or different ethnicities or neurodivergence. Co-design can be such a valuable and creative source of research ideas because it's not constrained by your own biases, right? I construct an experiment that is influenced by the way that I'm already thinking, which is based on my experiences. So I think, scientists like to think we're really objective, but really we just have to acknowledge that we're just as biased as everybody else. And what we all need to do is be aware of those biases. Sorry, I don't know if I answered your question.
Donna, so it's 4. I'll just keep.
Thank you. Some of that might have been answered. I had another question, but I'm going to about race and eugenics and Indigenous cultures, but I'll move on to my other one. I'm interested in both Trevor's work, and I've followed your work for a long time, and I find it really absolutely, it answers a lot of their questions, and in fact puts into practice a lot of the questions that Anina is talking about. What I'm interested in is in terms of the ways in which artists perceive colour. But you talk a lot about perception, but how do they make colour? So how do artists make colour, and how do we register or understand how that process happens? But how do they also make form? So those types of ways of seeing and acting in a physical, tactile way is very, very different. I live with an artist, see it every day. It's very, very different to the ways in which I see these things. So I'm interested in terms of the ways in which artists do this, both in a material sense, but also in a digital sense, given that we are now using text prompts to create colour and form and all of these other things we've been talking about this morning. And how can we actually capture or understand that process a bit better, and whether or not your work, I think, Trevor, is potentially doing that already, but maybe not understood in that way. But how can perhaps this idea of co-research or whatever reveal some of these different perceptions of making?
It's a huge question. I'll answer it with some very specific kind of stories. So I do a lot of photography, and sometimes I'll make an image, and then someone will say, well, is that what it really looked like? And I'll be like, I have no idea what the constitute, what kind of neurons, whatever you have in your brain, and what kind of cells you have, like in your retina. That question is fundamentally a bizarre question, although it kind of makes sense. But so that's one thing in terms of working with color. When you're making art objects, again, if I'm working with photography, you're making an object. So I print things and they go on walls and things like that. And when I'm doing the color on a print, I'm usually working across multiple prints and iterating them, trying to get them to the color exactly that I want. And usually I know I'm done if I make 2 exact prints that are functionally identical in terms of how they're printed, and I put them next to each other, and the one on the right looks different than the one on the left, and then I take the left and I put it on the right, and then it flips back over. So when we get into the zone where the juxtaposition of the 2 images is the main thing that's creating the color difference in my mind, then I know I'm done, because you kind of gotten to that limit. And in terms of composition, I think everybody works really differently. I mean, I personally was first trained as a composer, so writing music, and so I weirdly think about composition very musically and thinking about what is the relationship between harmony and dissonance that I want to have in an image, and how do you structure that and that kind of thing.
Can I just
Yes,
butt in there?
please.
So it's really interesting to hear you talking about how something changes when it's on the left or the right, because we have attentional biases, right? And so there's a laterality difference in, if you're looking straight ahead, something being presented on the left side of space to the right side of space. So you're introspecting that you actually see it completely different, like not completely differently, but that's the point at which you know that it's own. Yeah, that's really interesting.
That's a little hack I taught myself.
So I know there are more questions that you'd like to ask, and there will be a chance, especially for those who are going to be here over multiple days, to interact because we're going to have a last session in which we all talk about some of these issues. But I slightly horrifiedly look at my watch and realise we're slightly over time, and so we'd better wrap up. But can I ask you all to thank Trevor and Anina for a really fascinating... We're back at 2 o'clock for the second session.